All right, let's take a look at workbook 5G and H. 5G is all about the ballistic pendulum. So we have a small dart of mass m is launched at an angle phi above the horizontal with an initial speed of v naught. At the moment it reaches the highest point in its path and is moving horizontally, it collides with and sticks to a wooden block of mass m, capital M, that is suspended at the end of a string of negligible mass. Obviously, it just means that the mass of the string doesn't matter. We can neglect it. The center of the block is a distance L below the pivot point of the string. The block and the dart then swing up until the string makes an angle of theta with the vertical as shown at the right. We're going to ignore air resistance. So we have our little diagram here. You can see the dart is fired at an angle, and just as it gets to the top, it hits this pendulum that's sitting there. It sticks into the pendulum, and then it flies. It causes the pendulum to fly up into the air at this angle. So part A, number one, sketch a horizontal and vertical velocity versus time graph from the time the dart is launched to the time it hits the block. So the horizontal velocity, if you remember from back in the day, when things are fired or launched at an angle, the horizontal velocity doesn't change, especially if we are ignoring air resistance. So this is qualitative. There's no values associated with it, but we do know it's going to the right. And so we'll represent this as a positive constant value. This part, the v cosine of phi, is not absolutely necessary at this time, but it does kind of help if you want to draw the triangle diagram to help you see this. For the vertical velocity though, which in our little triangle is going to be v cosine or v sine of phi, as you know, as something is launched upward, the vertical velocity will be starting off as large and it will decrease at a constant rate of negative 9.8 meters per second squared. So it's going to go down, 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 down until it gets to the top of the path, and then at that point the velocity would be 0. And if it didn't hit the block, then the velocity would continue going in the opposite direction, going downward and increasing in speed. But because it hit the block, it basically stopped. Part A, letter 2, determine the speed of the dart just below or just before it strikes the block. Your answer should only include all those constants and physical constants as necessary. A lot of times you'll see stuff like this where they'll say you can use any of these that you want. And the thing is, those are the limits, but it doesn't mean you're going to use all of those necessarily. So as you can see, our answer is you're just going to do v cosine of phi. And why v cosine of phi? Because if you were to draw the triangle, you would see that, let's see, I could just draw it really quickly here. Where should I? Maybe I'll just try to squeeze it in this little spot here. So it's launched at an angle, v naught, and I'm going to draw my initial velocity in the x direction and velocity in the y direction. And here is my phi. And so the, here, that's probably good enough. The v in the speed of the dart before it strikes the block, right? So it's at this time the vertical velocity has shrunk down to 0 because it hits at the top. So we're really only concerned with the horizontal velocity, which is the adjacent side from the angle. And the adjacent side uses cosine. So if you were to do the trig, you would find it's v cosine of phi. Okay, so just a little throwback to first semester stuff, but that's going to be how it's always going to be. Something that we've talked about in the past is always fair game. Part B, identify the system by circling both the dart and the block, or and the box with the dotted line. Done. So here we go. It's a little vague. Should I have included this one? I don't know, but I didn't, or it's not. And I think it's because this is sort of looking into the future a little bit. Like when you started out, the block is hanging there and the dart is down there. So that's why it was drawn the way it was. Letter 2, sketch the momentum diagram for the systems, from the system from just before to just after the dart collides with the block. All right, so it doesn't really say much about the masses. It just says the wooden block has a mass of capital M, and the dart has a mass of lowercase m. It doesn't say anything about the relative masses. It just doesn't. And so when we draw it, like basically we just need to make sure that we know that the dart has it's going to be smaller. It's going to have it doesn't say it anywhere. So we just got to double check it just to make sure. Because if it did say anything about the mass, we need to represent that. But as far as I could tell, it doesn't at all. Yep. So what we do need to be sure of with the mass is whatever velocity we give it is all good. We know that the velocity of the block initially is going to be 0. But what I was about to say with the mass is whatever you do with the masses, the final momentum has to have the same area total. So the area here is 1, 2, 3, 4, 5, 6, 7 blocks tall by 1, 7 times 1. So our final momentum also has to be 7 blocks total. It doesn't have to be tall for reasons I'm about to say. But the thing that has to be true is the mass has to be consistent. So the mass of I made this 7 tall. This is 1 wide for mass, and the block is 6 wide. Therefore, the mass has to be a total of 7 blocks wide. I should stop saying blocks, squares. So the mass of the dart is 1 square wide, represented here. The mass of the block is 6 squares wide, and so therefore the final mass should be 7 squares wide, a total of 2. But the area has to be the same, so 7 tall means 7 wide here. Okay, like I said before, there's a lot to keep track of with these diagrams. So the argument. This is not a lot I could talk about here. There is a lot I could talk about here. But I will say a couple things. One, when you do this on the test, the AP test, a lot of times it doesn't matter if you've checked the correct answer. I mean, it does. Let me just put it that way. It does. But a lot of times it's not like you get 1 point for choosing the correct answer. It's more like you lose a point if you choose the wrong answer. Okay, so you could check the right answer and leave everything blank and still get a 0, is my point. But if you choose the wrong answer and explain everything perfectly, you won't get a perfect score. Okay, so choosing the right answer is important, but your explanation is really important. So there's this checklist here that I think is very, very, very useful here. And I mentioned it in the previous one. But answer the question, make sure you state any laws that apply, connect those laws to the actual circumstances that we're dealing with. Did you compare the situation? Okay, so in this case, it's a before and after, right? Contrast the situations, what was different, and make sure throughout this you use the proper vocabulary, not just words that you make up or words that have a different meaning or connotation outside of physics. Okay, so again, this checklist is going to be important. I would say definitely maybe write it down or put it somewhere, make a note of it somehow. Okay. Letter H, experimental design. Carlos and Dominique have been challenged to design an experiment to determine the impulse given to a cart as it collides with a barrier using 2 different mathematical or graphical ways. Dominique sketches the following diagram of the laboratory setup and writes the procedure below. Okay, a word about procedures. There's a whole lot I could say about it, but to be brief, I want to point out that the situation here is different. The setup here is different than what we've done in our lab, and that's something to keep in mind. You can measure the same stuff, but using slightly different tools. So when you write your lab procedures, keep that in mind that you are not describing, for example, in our case, how to use vernier graphical analysis and the vernier carts. You want to describe that you are measuring velocity. Okay, measure velocity or calculate velocity or measure mass or measure something. Okay, you don't have to get into exactly all the little nitty-gritty details about how to do it. Okay, so this is the setup that they've got, and then we got this whole bunch of white space, and then we got this setup here. So Dominique's procedure here is very reminiscent of a lot of common mistakes that students make. Gather raw materials. Some science teachers pull their hair out when students start by saying, gather the materials. I don't. I mean, it's a very understandable mistake. It's just not necessary, like, at all. Because of course you're going to gather the materials. I don't know, it's just not at all necessary for somebody in high school who's done labs before, or college or beyond. So what you want to get straight to it. You're in a lab, you're in a situation, you've got all your tools ready to go. Start by recording the mass of the cart. Okay, it's obvious that you don't need to state the obvious. It's obvious you're going to have a scale. It's obvious you've already had the materials listed somewhere else. I scroll up, you can see it. Okay, so check this out. Look at what they've crossed out, what they kept. Look at what they've changed, and just they crossed out 9 steps. All right, so clean up. That's another one. It's like, oh yeah, we know. You don't have to write that out. Okay, focus on what is it, like, what is the object you're going to be working with? The cart in this case, right? What are you going to do? Okay, so every step usually has a verb. Determine it. Stop recording. Give the cart a push. Okay, begin recording. Step 2 is record. Okay, every step should have a verb and a noun, an object. What tool are you using? So most of the steps will have some sort of measuring tool mentioned. How are you going to do this? And what are you going to measure? What is the measurement you're going to take? All right, what exactly are you doing? Not just the action, but like why? What measurement are you taking? And usually all the steps are going to have some of those or all of those. Okay, so check that out. Get your procedure writing. This is something to work on, and it's something that you'll be working on for forever. It's just one of those things. Even if you go into science, I mean, I guess if you don't go into science, but even then, outside of science, writing procedures is something that a lot of people do in a lot of situations, a lot of jobs and careers. Part B, sketch the graph of the velocity as a function of time and record. Why did I just say record? As a function of time, and the forces as a function of time should look like for the time just before the collision or just after the collision. Okay, so these should look relative, or at least the one on the left should look familiar to you. You've done a lab where you saw collisions happening. And this is the basic parts of it. There's usually 3 parts that are important. You have your initial velocity, where the velocity is more or less constant. Okay, on your graphs, they were slightly decreasing because of friction that actually exists. So that's a flat part. You have the collision, which is a curvy change in the velocity. And then you have another flat part where the velocity, the final velocity, is more or less not changing again. Again, the final velocity in the lab does slightly change towards 0, but that's because of friction. So you should have that. And the carts in this case, it bounced, and so you want to indicate that it's going in one direction. There was a collision, and it bounced into the other direction. Okay. The force diagram over time, we didn't look into those that much, but we've seen them before. This is quantitative. No, I'm sorry, this is qualitative. There's no numbers on these graphs. But what you need to do is just make sure that the force and time, the force is applied during the time of impact. So the time of impact, if you were to count the squares over here, the time of impact should start at the same number of squares, and it should end when the velocity became constant. So it's going to be some force negative because it's changing, it's pushing it backwards. That's important. Okay, so if it's going positive and you want it to go negative, if you want the cart to go negative, you have to push in the negative direction. So that's why this force diagram is going in the negative direction. The time starts when the change in velocity starts here. The push time ends when the velocity stops changing. Okay, so those are the 2 important things to keep in mind here. The actual amount of force is not given. So you could have gone down a little bit, you could have gone down a lot more, it's up to you. But the time and the direction are definitely important based on the information we have. And this explains it. It talks about how impulse is a change in momentum. And it goes into that. It talks about the area, which we're not getting into because there's no numbers to calculate. All right, so that should help. And if not, you got